Welcome to the fifth and final presentation in Unit 3 entitled You Get Out What You Put In. And you see right here we have the Madden stats for Jadeveon Clowney right there, and we see his rookie year statistics right here, including 7 tackles, only 5 solo, 0 sacks. And this is what he was supposed to do. So he didn't get out so much, maybe he didn't put as much in. It says efficiency is doing the right things. Efficiency is doing things right. Effectiveness is doing the right things. So, the learning goals for this presentation are that students will be able to explain why energy input does not equal energy output and to calculate the efficiency of an engine. So, here's what we know. We know that energy must be conserved. It's always conserved. We also know that we have work, kinetic energy, gravitational potential, and elastic energy, amongst other things like heat and thermal energy and chemical potential energy and all these other types of energy. So because of that, we know that we learned in the lab that energy can be transferred between two forms. As the kinetic energy increases, the gravitational potential energy decreases, and the total energy of the system is constant. So the total energy, if you have throw a ball up in the air, the ball can have both. It's above the ground, so it's going to have some sort of GPE, and it's moving because it has velocity, so it's going to have some sort of KE. Because of that, things can have more than one type of energy, so oftentimes we refer to the total energy of a system. The total energy of the system is often referred to as the mechanical energy of the system. The mechanical energy is the sum of the kinetic and the potential. Now notice this is all of the potentials. So that could be chemical potential energy, it could be elastic potential energy, it could be gravitational potential energy, it could be all of those potential energies combined. So it says mechanical energy is a unit of energy. What should mechanical energy be measured in? And that would be the joule. So it says write an expression illustrating the conservation of energy using mechanical energy. So conservation of energy says that the total energy must be conserved, and mechanical energy is an expression for total energy. So because of that, we can say that mechanical energy 1 equals mechanical energy 2. So if a roller coaster has a certain amount of energy right here, it's going to have the same amount of energy right here. The difference is here it's mostly all gravitational potential energy, and here it's almost all kinetic. It says a box has a total of 500 joules of mechanical energy when moving with 200 joules of kinetic energy. How much potential energy is stored? Now the formula we have is that the mechanical energy is equal to the kinetic energy plus the potential energy. We said we have here 500 joules of mechanical energy and 200 joules of kinetic energy. Because of that, we can say 500 equals 200 plus PE. We subtract 200 from both sides, and when we do that, we get the potential energy is equal to 300 joules. Okay, what is the mechanical energy of the system given the experimental data below? So we have experimental data. It says at some sort of time t, these are the measurements that we have. So we have a gravitational potential energy if it looks like 4. We have a elastic potential energy if it looks like 10. And we have a kinetic energy if it looks like 25. Remember, mechanical energy is the sum of the kinetic and the potential energies. And this potential energy is referring to all potential energy. So when we solve for the mechanical energy in this case, the mechanical energy would be 25, which is our kinetic energy, plus 10 plus 4. As a result of that, you can say that the total energy is 39 joules. So now work output and work input. Even though energy is always conserved, you don't always get the same amount of work out as you put work in. Instead, what you have is you always lose some energy. Now, the energy is not lost. It's converted into things like heat, sound, vibrations, things like that. It's not that the energy disappears. It's just going into non-useful work. So the missing work is usually converted into heat because of friction. And you see that most often with cars. If you were to be driving along in a car, you have kinetic energy. If you have kinetic energy and all of a sudden you slam on the brakes, it looks like that energy has been destroyed. But instead, that energy was converted into friction by friction into heat. So if you were to come touch the brake pads right here, they would be extremely hot because all of that kinetic energy has been converted into heat. If you can find a way to reduce friction, most of the time that makes reactions more efficient. So if you're looking at something like trying to get a train from here to say, I don't know, from let's say Dallas to Los Angeles, that's a long way. If you could somehow reduce the friction of the train along the track, you could save a lot of fuel. And a lot of times they do that whenever you see things that are high-speed trains, they actually hover above the track trying to reduce friction. So we have efficiency. Efficiency is the ratio of work output to work input. So basically you take the work that you get out, and this is the work that you put in, and you multiply it by 100 to convert it to percentage. What you'll realize is that you can never exceed, you can never be greater than 100%. That will never happen. Okay, you can only put out at least what you put in. You can't get any more out than what you put in. So it says efficiency is expressed as a percent with no real units. Explain why. The reason is you're taking work, which is measured in joules, and you're dividing it by work, which is measured in joules. As a result, joules divided by joules cancels out, and there are no units. Now, whenever you multiply it by 100, you're actually converting it into a percentage. This is that the 2015 Prius has greater efficiency than the 2009 Prius, assuming they have the same tank of gas. What does this mean in terms of work? So, let's say they have the same amount of work output and work input. So they have the same tank of gas, so they put the same amount of energy into the car. But since the 2009 Prius has a lower efficiency, that means it doesn't get nearly the work output that the 2015 Prius does. So in terms of work, that means I get more work output whenever I have the 2015, which in real terms means if I get more work output, that the car can actually travel faster, or not travel faster, it can travel further on a tank of gas. So what that means is that it'll have an elevated miles per gallon rating. Now calculate the efficiency of an engine in which 500 joules of work results in 450 joules of output. And that would actually be a very, very efficient engine. So we have efficiency is equal to work output divided by work input times 100. Whenever you do this, you get 450 divided by 500 times 100, and then that ends up being about 90%, which is very, very efficient. Most car engines that you have are roughly 20 to 25% efficient, even the best ones. It says, can a car ever be 100% efficient? Justify your answer. And the answer is, of course, no. And the reason why is you have friction between the tires and the road. In addition to that, you have air currents or air resistance that slows down the car. And some people say, well, if you have a tube that you don't have any air in, you can take out air resistance. And if you can get the car to hover above the ground, there'd be no friction. And that's true. But friction is required to turn. Without any friction, there'd be no turning. And as a result of that, a car, the way you traditionally think of it, cannot have 100% efficiency.